Hello. Okay. Hello. Welcome to a new problem. We're gonna do this problem called 110 balanced binary tree. Um, should be like yeah. I did solve this before, but that was probably a long time ago, and I'm kind of redoing everything. Just to make sure just to make sure like I learn it and stuff like that. But I actually forgot how to do this. But I think yesterday's problem that I did will help me with this. So yeah, let's just get started. So, given a binary tree, determine if it's height balanced. So, we're given, I'm guessing, roots of BT. And for output, I'm just gonna, yeah, it's a bool. So if, bool if height balanced or not. And then to note, we can say that, oh, what the hell is height balanced? I don't know. I don't know either at all. So height balanced means that binary tree, where okay, so depth. Oh, okay, so what is height balanced? Is height balanced? Or depth of two subtrees of every node is not more than equal to more than one. Okay, is not more than one. Okay, so that's cool. So I think that makes sense. Let's do an example, I guess. Or maybe let's add some questions, actually. Oops. So I can say, I guess, can we be given a binary tree with no nodes? Let's see. We're sure that's true. Yeah, we can receive a binary tree with no nodes. Okay, cool. I don't think the value of the binary tree matters, like the nodes in the binary tree. So yes, min size is equal to 0. So cool. So we know what the input output is. We know what a height balanced is. Basically, yeah, we gotta check if the height is like not more than 1. So yeah, and then the questions. Yeah, we went through the questions. So let's go through some examples. For me, I'm just going to go through a Jamboard and kind of go over like examples that LeetCode does, because I don't want to make my own. Well, I could. I'm just gonna do it. So 1, and no, it's gonna be the same thing but different numbers. So 1, 2, and then 3, and 4, and then 5. Okay, they point like this, right? And so let's go figure out if this is height balanced. Well, as you can already tell, this has the right has a height of, oops, the right has a height of 2. It says height of 1. So this is like true, I guess, right? But let's kind of go over it in like a coding type of way, I guess. So I'm guessing we're just getting the height of each, get the height of each subtree. So this height of this whole subtree starting from the root is 3, right? Let's get the height of this and this and this, right? So let's go left and right. So we go left. We know that this has a height of 1 because there's nothing here, right? Now here, we don't know what the height is still because we still have to go through here. Or we have to go through these, right? So from the right, we go down left once more. And then, okay, now we're at this 4. And 4 is like, okay, I don't have any more children, so my height's still 1, right? It returns back to the 3. And now that we're done with this 4, let's go to the right, to this 5. 5 says, I don't have anything here. So my height's 1, right? I go back. Then I guess we get the max of either 1 or 1. I think. Yeah, that makes sense. Like, what's the height of this subtree, right? Max height of the subtree. And then we're like, okay, so my max is 1. I counted my other subtrees. Let's just say that these are subtrees, right? So I'm going to say my height is my subtrees. So I'm gonna say max subtree height plus 1, right? That gets returned to this one, right? And then yeah, that's pretty much it. Yeah, we're gonna do that basically. And then so I got a notification. And so yeah, that's what's gonna happen. And then I think at every node we should be like in my balance or something like that, or is my left and right, yeah, is my left and right larger, like difference more than 1, right? But yeah, let's do an example where it's obviously unbalanced. So it's like 1, like 2, like 3, right? And then 4, 5, and then 6 and 7, right? Okay, so first off, we kind of already know that it's not balanced. If we just look at the height, right? The left has a height, starting from the root, the height is here's just 2. The height here is like 1, 2, 3, 4, and that's a difference more than 1. So yeah, so this is not balanced, right? So we already know that. Let's kind of go through it with code. So start left, and then left has height of 1, returns 1, right? It should return 1, and then boom, goes there. I should make that different color. 1, and then here we go to the right subtree. So we got to go through all this again. Now we don't know what the height of this subtree is, so we got to go deep to find the height. So this is 4. This should return 1. Which goes back up to this 3. And then this 5, we don't know the height of this 5 because to go through this subtree again, right? And so this 5 doesn't know its height, so we have to go down. This should return 1, should also return 1. And then they return back to the 5, which says that my left and right heights are 1. So that means that my height is 2. Okay. My height is 2, and that returns back to the 3. And now the 3 is like, okay, I know my height of my left and right, so I'm gonna take the max, which is this 2. So my height is now 3 because I plus 1, right? Because of the 2. And now this 3 knows its height. My height is 3 because yeah, it doesn't have to be. I mean, the value doesn't correspond to the height. And then okay, so my height is 3. So 1, you're gonna get back my height, which is 3. And so yeah. And then, but I think somewhere, it doesn't happen here. It happens at I think it happens right here, at this. So basically, it happens when we return to the node. So yeah, I think it happens at this node, but it doesn't happen here because these have heights of 2 and 1. So I think we have to check. I think here, once we get the left and right, we have to check if the max of 2 and 1 minus the min 2 and 1 is more than equal to, no, is more than 1. Right, we gotta do that. And then if that's true, then we just return that it's false. But if it's true, then we just keep going, right? And then this happens here when we reach this, I'm pretty sure, because the max is 3 and the min is 1. And so if that difference is more than 1, then return false. I should write that down kind of made that in my mind. Okay, we're gonna do through some examples. So for our plan, no, for our match, because we kind of already did the example and we kind of matched. So do max of right left minus min of right left more than one. This should help us find if balanced or not, and do it at every root. So yeah, and then we're also going to do depth first search. Then I'm thinking that other than the node, we're going to carry depth. Are we going to return the depth? I don't know. Oh no, hold up. Okay, so I have to go somewhere, but I don't think this is a semantical issue. I think we don't need to need to add the depth in the recursion because we're just gonna just return the depth and stuff like that. So yeah, because this is what I did here, where we just kind of return the depth and to the left, right? Okay, so I don't know how to code this now. So that's cool. So the plan, let's make a plan. So this is for the function to run. Okay, so I was gonna have depth first search in the function. We're gonna give it the node. And then basically if not node, then return 0, I guess. And then we can say, yeah, we can turn 0 because we should return 0 because what if it's like there's no children, right? It's a leaf node. And then the process that I'm trying to look at is we're gonna say that left plus return left plus right. We're gonna turn the max of left and right plus 1. That's our height, right? So we're gonna turn our height or depth. So subtree depth is equal to that. And then so once we got that, before that we had to just call. So left is equal to the fs of no. Yeah, and then we had to return subtree depth, right? And that's how we get left is equal to the fs of no dot left, and that's how we get the right value, which is dfs no dot right, because in recursion we just basically return the subtree depth, right? So there you go. And then what do we need to do? Trying to think. So what I'm thinking about is from here we just get the subtree depth, right? So I think through this process, let's go through it. We return 1 to this 5 as it's left because it returns 0. Yeah, because this 6 has no children, so it's 0 0. And then this 6 says that left is equal to 0, right is equal to 0, and it says that its subtree depth is 1, right? And then same thing with this. So now this 5 has left equal to 1 or 1 plus 1, so that's 2. And then what am I trying to say? Yeah, so this definitely works, but I think we need a case where once we get the left and right, we got to compare. So So I think we gotta say like we gotta compare somehow where the max of left and right minus min of left and right, right? So if this equals, so if more than 1, then we gotta return true somehow. So, So I think we need to also have another variable. So a variable to hold bool, result bool. So I think I can have it where we can have like is balanced equal to a boolean, which is true. And then if that, and then we can reference it here. So non-local is balanced. And then I guess yeah, if this is true, if it's more than 1, then it's not balanced. So you say is balanced is false, and then we kind of just return, I think. Or we can just keep on going, but we just keep going, and then in the end, we're going to return is balanced. And then within this other function, we have to call DFS with the root. Right? That's kind of it. I mean, it's kind of clean, but I don't know what this part is. But maybe I guess we can say, so we can keep checking, I guess, even if we keep going. So if is balanced, if not is balanced, basically if it's false, then just return. It's kind of messy. I don't like how it's written. But in a way, I feel like if this wasn't Python, I would have to just return. I don't know. This is kind of weird, but I think this works. Like it sounds like it works. Because we go up here, it's 3. So right is equal to 3, and then left is equal to 1, right? And then we just compare. So if max left and right minus the min. So if 3 minus 1 is more than 1, which is it's 2. So 2 is more than 1, then set is balanced is false, then return. But I think this case is good. I don't know. Like if we just keep going on with like recursion and stuff like that, this will stop the recursion instantly if we just find that when we do recurse that is balance is false, then we just stop recursion, right? I think this is fine, but in other languages might be really bad. But we're writing in Python, so who cares? I think this should work. Yeah. I'm pretty sure there's a better way to do it, where we kind of also like store like is balanced in here, and then we check is balanced is true or false, I guess. Like I think I could write it like that. Yeah, so okay, so let's say that's true here. No, I'm not doing it like that. I'll just do it like this. I like it like that. So okay, so let's go ahead and kind of code it up. This function is going to be named check get is balanced, I guess, and it's going to get our input as a binary tree, so root, and then we're going to have that first search function. It's going to take in a node, and then we're going to call that first search with the root, and then we're going to basically return is balanced, and then we're going to I should not do this, so I'm gonna pass these for now because I need to set up some stuff. We're not coding yet. And then I guess I'm gonna make my tree node class. Um, okay. Okay, let's go and make our driver code. So test case 1, I'm just gonna pause and make my test cases. All right, so I'm kind of done with my test cases, just copy and pasting. So get is balanced. We're gonna call it and print out its return value with test case 2. And yeah, so this should return true, and this should return false, because we just kind of did this problem here. So they should return false because they're imbalanced. But basically for test case 1, I just did this 3 and then 4. Right, so this is 2, this is 1. So it's check, right, that it does work, or that it's true. It's true. So yeah, we're gonna test that, and then let's go ahead and kind of code our code. Well, first off, we said that our driver, in our plan, that we need to have is a boolean, which is balanced, set to true, and then we're going to in the get is balance function, we're going to call our DFS and give it the argument of root, and then we're going to return is balanced. So yeah. Yeah, and then in our depth first search function, we're going to be changing is balanced, the state of is balanced, depending on the max of its left and right. Like yeah, if the right and left difference is more than 1, so we're going to reference it. So non-local is balanced, and then I guess we're going to call our left. No, first things first, I need to chill. So first things first, if the node is null, then we're going to return 0. If not node, then return 0. And then in the case, yeah, and then we're going to get its left and right by calling that first search on its left and right. And then we're going to get the subtree depth of the subtree that we're at, which is the node, which is the max of left and right plus 1. And then we're going to return subtree depth. That's how we kind of get left and right, because in just like I said, if we hit a node with no left and right, then return 0 from its left and right, as seen here. And then to get the depth of the whole tree, or the subtree, is plus 1 with its max of left and right. Right. So that's why we say the left is equal to depth first search of node left and right, so we can get the subtree depth of that subtree, which is left and right, right? And then other than that, we kind of want to check this, right? So if max left and right, so if the max minus the min of either subtree's depths is when we get the difference, and if that's more than 1, then we're gonna say that the subtree, which is node, is not balanced. So we're gonna say false, and then we're gonna basically return. We're gonna stop. But then there's going to be, or there could be a case where we'd still do recursion. So we still do recursion, and we already found that this whole tree is not balanced. So we're gonna say, so if is balanced, so if not is balanced, basically, then we're just gonna return. Kind of messy, like I said before, but I guess it does work. So we're just going to run this and see if it works. So we should get true and false. Hopefully this works. Interesting. So I'll get balance print TC1. Okay. Oops. I should have read it more. Cannot access local value because we do this before anything else, which is not good. Okay, so it should work now. Yeah, true and false. Okay, so it does work, but again, it's kind of messy, but I actually solved it using my solution, so I'm kind of happy about that without looking up the video. So amazing, cool. So let's see if it actually works in LeetCode. Oh, this might be an issue. Not sure if it is an issue. We'll see. Pretty sure it is. No, it's not. Okay, cool. Accepted, submit. So it's saying that we're comparing. So in this case, left and right are both none. So what does that mean? That shouldn't be the case because we do this. We just return 0. What's happening? Can I see what this is? Maybe I do this first. Because it's just returning nothing. So if I say that this is first, then it shouldn't skip it. Still the same thing. Interesting. Trying to figure out how. Okay, left and right. Okay. It should return 0, 0. That's 1. I guess I can say like, so print left and right. See what happens here. Is so if is balanced equal to false. Maybe that. No. What if I just stop it here? Just like don't even do anything like that. You just keep going. Okay. Okay, so that's the issue. Something about that. So it kept going in the recursion. Interesting. I guess I can submit this, but I don't know. I think that's fine. I think that's okay. But like I kind of want a solution where it's like it stops right there. Like once we like the instant that we find that its balance is false, then we just stop looping or something like that. I don't know. Or we just stop recursion. Just want to see. So I don't know. That's so weird. So I'm just gonna leave it at that. I'm probably want to watch a video about like, cause there's probably like a video that does that. So I'll just like watch it and then learn from it. But yeah, I solved the problem pretty cool by myself this time, which is awesome. Cause I've been struggling with these problems for a while now. So yeah, to review its complexities for time, I think it's just O of n, or like how many nodes there are in the tree, because we have to go through each one once. Yeah, we go through them once. And then for time, it's O of n, because wait, I already said that. Yeah, for time, it's O of n. For space, yes, you could say. For recursion, I don't know what the space is, but we're just using variables to solve this problem. So like, it's balanced in left and right, which holds integer variables, which holds integer values. And yeah, so I think it's O1 extra space. Yeah, that's pretty much it.